Typically, the inner solar system sees only a few comets each year. However, in late 2025, 7 major objects are plunging inward simultaneously, including the interstellar giant 3E Atlas, which is expanding daily. Scientists are charting this incredible swarm, something unseen since the dawn of modern telescopes, tracking their paths as they speed by Earth and the Sun within a compact 6-month period. Some speculate that this flurry of activity might even trigger solar storms, and one of these comets could become bright enough for naked eye viewing. But what is causing so many to arrive together, and what potential for danger or awe does this celestial traffic jam hold? Let's explore the most unique comet schedule of our lifetime. Having 7 major comets pack the inner solar system in one season is nearly unprecedented. Typically, astronomers may find 1 or 2 bright comets passing near enough for detailed study, or perhaps 3 if surveys get fortunate. Yet, a year featuring 7, all plunging inward over a few short months, is an event that is remarkable, even in 100 years of astronomical records. From the beginning of systematic sky surveys like Pan-STARRS Linear and the Atlas Project, no season has seen this level of activity. The previous time comet numbers were even close to this. Telescopes still use glass plates for recording, and the majority of discoveries were made by chance or through casual conversation. Today, it's more than just the sheer count that is so striking. This particular swarm stands out because it's not a gradual stream over many years. It is an intense influx, with every object weaving through the inner solar system one after another. A few are arriving from the most distant regions, some are returning periodically, and 3E Atlas doesn't originate from our solar system whatsoever. That single interstellar wildcard would make headlines in any given year, but when combined with 6 other significant comets, the chances of this happening are incredibly slim. Statistically speaking, an average year since 2000 has featured only 1 comet becoming visible to the naked eye, and a couple of others seen just with binoculars or telescopes. Numerous years pass with only dim, faraway blurs to see. Even during what are called comet showers, short intervals when multiple objects show up together, a number like 7 is practically missing from modern records. Based on the minor planet centers, public data, not one season since the digital age started has featured more than 4 major comets reaching perihelion within 2 astronomical units. And this doesn't even account for the ecliptic alignment that this particular group is exhibiting. To provide some context, while comet discoveries have skyrocketed recently thanks to robotic sky surveys, the great majority end up being faint, far off, or fleeting. Bright and easily observable comets are still quite uncommon. The 2025 arrival is so exceptional that some astronomers are calling it a statistical anomaly, the type of occurrence that may take place only once every several generations. This is why we're looking at more than just a list of objects. It's a true phenomenon. It is a genuine swarm that defies our expectations of the solar system's normal cadence. With this many icy travelers showing up almost simultaneously, astronomers are now handling it as one single event with multiple acts. Their focus has moved from studying single comets to monitoring their combined dance through space. They are studying how their orbits' alignments and encounters with the Sun could possibly interact. This unique convergence is what's driving both the scientific buzz and public excitement. Before we get into the specifics of terms like perihelion, superior conjunction, and ecliptic alignment, it is worth reflecting on the rarity of witnessing 7 major comets performing on the cosmic stage together. C 2022-2 N2 Pan-STARRS kicks off the 2025 comet season, arriving at perihelion on July 31st at a distance of 3.82 astronomical units from the Sun. Its faraway trajectory places it far beyond Mars, where the sunlight is faint and only highly sensitive telescopes are able to follow its journey. Pan-STARRS establishes the outer limit for this incoming swarm. It's a calm beginning before more spectacular arrivals. Next is C2025 R2 Swan. Found on September 11th, it speeds to perihelion only a day later, on September 12th, at 0.50 astronomical units. The main event occurs on October 21st as Swan glides past Earth at only 0.25 astronomical units, or about 37 million kilometers. This proximity makes it an excellent target for viewing, particularly in the northern hemisphere's pre-dawn sky. Swan's swift motion and unique geometry provide a special opportunity to observe a comet's real-time interaction with the Sun and Earth. 414 P stereo is set to circle the Sun on September 27th at a perihelion of 0.52 astronomical units. Its orbital path drops beneath the ecliptic plane, presenting a tough challenge for ground-based observatories as it's frequently obscured by the Sun's glare. The Stereo, mission's own namesake comet, is a better fit for spacecraft observation. Its low trajectory presents a unique vantage point for solar research. C2025 K1 Atlas is arriving next, getting to perihelion on October 8th at a mere 0.33 astronomical units, which is closer than Mercury ever gets to the Sun. This close solar flyby means Atlas will experience swift changes, making it a vital object for tracking outbursts and tail formation. Its nearness to the Sun puts it at the very center of the swarm's action. 3 Atlas, our interstellar guest, will arrive at Superior Conjunction on October 21st, crossing behind the Sun from our viewpoint on Earth. Perihelion comes after on October 29th at 136 astronomical units, which is just inside Mars's orbit. With an inclination around 5 degrees, 3 Atlas stays close to the ecliptic, sharing celestial space with the planets and the other comets. For a number of days, 3 Atlas and Swan will both hold key positions for solar interaction studies, although neither is simple to see. C2025 A6 Lemmon reaches its peak at perihelion on November 8th at 0.53 astronomical units. Its orbit allows it to be seen in the evening sky post-sunset, giving us one of the best observation opportunities of the entire group. Predictions indicate it might achieve a magnitude 4 or perhaps even 3.5, possibly making it visible to the naked eye for those in the north in early November. 240p NEAT finishes the lineup and will get to perihelion on December 19th at 212 astronomical units. As a periodic object, it is dimmer and more distant, yet its appearance underscores the packed conditions of the inner solar system as the year concludes. Each comet's trajectory, perihelion date, and its relation to the ecliptic plane form a very crowded schedule, preparing the scene for the solar interactions to come. Comet tails are much more than just cosmic displays. They are living chronicles of the invisible energies operating within our solar system. When a comet gets near the Sun, the solar radiation warms its nucleus, which then releases gas and dust to create 2 separate tails, a wide pale dust tail and a thin electric blue ion tail. The ion tail especially serves as a direct link to the Sun's own magnetic field. It consists of charged particles carried off by the solar wind, a continuous stream of plasma, and magnetic fields flowing from the Sun at hundreds of kilometers per second. But that ion tail is not a permanent feature. It can be detached in a moment, a process referred to as a tail disconnection event. The science behind this phenomenon is based in magnetic reconnection. While a comet travels through the solar wind, it can run into sudden shifts in the interplanetary magnetic field, such as from a coronal mass ejection or when crossing the heliospheric current sheet. These are not smooth changes. The magnetic field might rotate by 90 degrees or more within minutes, and when that occurs, the comet's plasma environment is unable to adjust. The old tail gets severed and drifts away into space, while a brand new tail starts to form, aligned perfectly with the solar wind's new direction. One of the most stunning examples of this was recorded in April 2007 as the Stereo spacecraft observed a CME impacting comet Enki. The ion tail was cleanly cut with a clear gap appearing near its nucleus and the old tail just floating off a perfect textbook case that mirrored magnetohydrodynamic simulations almost exactly. These events are not uncommon during the solar maximum, with multiple comets heading near the ecliptic plane in late 2025. The chances of seeing a live disconnection are greater than they've ever been. The dust tail, however, is not as impacted by these magnetic events. It is controlled by sunlight and by gravity, not by magnetism. Only the strongest CMEs can alter or shorten a dust tail, typically by blowing away a section of the coma or altering its outflow. For the majority of skywatchers, the ion tail's abrupt breaks and subsequent regrowth are the key signature to look for. It's a direct signal of the sun's powerful energy in action written out across millions of kilometers of deep space. Solar physicists are observing this comet swarm with both excitement and a little apprehension, and not merely for the show. Behind the public view, a serious debate is unfolding about what these close flybys might mean for the sun's own activity. Certain research teams, particularly the NASA CCMC modeling group, propose that the sharp increase in cometary plasma and dust from these ecliptic-aligned comets could potentially push the sun toward more intense and frequent outbursts. Their models indicate that when a very active comet moves through the heliospheric current sheet or travels through a coronal mass ejection, the magnetic structure can change very quickly, sometimes setting off a classic tail disconnection. In these simulations, the sun's magnetic field lines wrap around the comet, and if a CME passes at the correct angle, the ion tail is snapped off occasionally within just a few minutes. The CCMC's MHD simulations propose that with several comets involved, especially at solar maximum, the probability of seeing numerous dramatic tail severings increases, and the extra plasma might even help create new instabilities within the solar wind. But not all experts are convinced. The Solar Orbiter and Parker Solar Probe teams cite their own in situ data, stating that most tail disruptions are much more subtle than the computer models suggest. They have documented many minor twists and bends in comet tails that didn't become full-blown disconnections, even when strong CME events occurred. Their direct field measurements indicate that small-scale turbulence, micro-reconnection, and the inherent variability of the solar wind can each be a factor, sometimes more important than a huge headline-making CME. From their perspective, the sun's own magnetic cycles and its large-scale field reversals are the true primary drivers. They see comets as more like passive markers than active participants, and they warn against exaggerating the risk to our satellites or power grids, pointing out that even with the 2007 Encke event, there was a negligible operational impact. However, with CME rates projected to reach 2 to 5 each week during the late 2025 solar maximum, the two sides do agree on one key thing. This is an incredible opportunity to validate their theories in real time. Space weather agencies are increasing their monitoring efforts, and citizen scientists are gearing up for a worldwide campaign. If a massive tail disconnection does happen while a comet is visible, observers from backyard scopes to spacecraft will be poised to capture it. For now, the discussion has made everyone's focus sharper. Every single new CME and every strange twist in a tail could shift the balance in this continuing scientific disagreement. When scientists initially calculated the orbit for 3I Atlas, the figures didn't match any known pattern from local comets. Its path is hyperbolic with an eccentricity far greater than 1. This means it isn't simply paying a visit, it is traveling through our system, never to come back. That fact alone makes it unique. Only two other bodies, Oumuamua in 2017 and Borisov in 2019, were ever confirmed as interstellar before this one. But Atlas is different in several ways. Initial measurements from the Hubble and James Webb telescopes indicate a nucleus somewhere between 320 meters and 5.6 kilometers wide. But its coma, which is the halo of gas and dust, it's ejecting as it gets closer to the sun, has already expanded to roughly 700,000 kilometers across. That is almost the size of the planet Jupiter, and it is still growing week by week. Unlike most comets that spend ages locked in the far reaches of our solar system before one passed near the sun, Atlas originates from much farther, likely cast out from another star system, bringing material created in a different cosmic place. Its chemical makeup also stands out. Spectra show a coma that is dominated by carbon dioxide and other volatile gases, while water vapor is minimal and cyanide is found only in very faint amounts. These are chemical signatures that are rarely observed in such high quantities on our local comets. The object's movement is equally revealing. It came into the solar system at a very sharp angle, grazing the ecliptic plane by only about 5 degrees at a speed that confirms its foreign origins. The potential scientific reward is immense. Every single observation offers a chance to contrast the building blocks of distant star systems with what we have in our own, and there's more to gain than just chemistry. As Atlas swings around the sun, it will leave a trail of dust and debris that Earth might actually intersect in 2026, a special opportunity for planetary defense groups to study interstellar matter up close. The tale of 3E showed Atlas is still being written, but it is already transforming what we understand about the true boundaries of our solar system. From late October into early November 2025, the heavens present a fantastic window for comet observers. No special gear is needed, just a clear sky and good timing. The spectacle kicks off before dawn on October 21st, when C-2025 R2 Swan makes its closest approach to Earth, flying by at around 0.25 astronomical units. Even with just a simple pair of binoculars, Swan's beautiful tail will appear to stretch an incredible 2.5 degrees, 5 times the apparent diameter of the full moon. Its head will shine at a magnitude 6 to 7, which is dim but still accessible for anyone who is willing to get up early and search the southeastern sky. For many northern latitudes, Swan will rise almost 40 degrees above the horizon during civil twilight, making it an ideal pre-dawn observation target. At the same time, 3E Atlas is set to pass behind the sun at its superior conjunction. While observatories on the ground will lose their view, the focus moves online. Solar observatories such as SOHO's LASCO C3 coronagraph will continue to watch, capturing both 3E Atlas and sometimes Swan as dim moving specks against the sun's extended atmosphere. These live video feeds are available to everyone. Anyone can participate in the search for abrupt changes, sudden outbursts, or possibly a tail disconnection event set off by a powerful solar storm. By the start of November C-2025, A6 Lemmon is going to take center stage in the evening sky. Projections put its brightness at magnitude 4, maybe even 3.5, which is bright enough to be seen with the naked eye from dark locations, particularly for observers in the northern hemisphere. Lemmon will be situated low in the southwest just after sunset, its coma and tail getting brighter nightly as it approaches perihelion on November 8th. For a lot of people, this may be the most easily seen comet in recent years. Whether you plan on using binoculars, a home telescope, or just your own eyes, this is truly a season to get outside and see the solar system in action. The ideal nights for observing are October 21st for Swan's flyby and November 6th through the 12th for Lemmon's peak performance. For any comets that are hiding near the sun, the world's coronagraphs will be your portal. which are just a simple mouse click away. Predicting comets is truly an exercise in humility. Regardless of how much data becomes available every single year, brightness estimates can be off by as much as 2 magnitudes or even more. A comet that is projected to shine at magnitude 3 might just fade to a 5 or 6, whereas a dim, ignored newcomer could suddenly flare up, surpassing all of the predictions. These kinds of surprises are due to factors that no computer model can completely account for: grain size within the dust, the specific mix of ices, or how sunlight gets through a crust that could be several meters thick. Even with our most advanced thermophysical models, a minor change in the solar heating or a single hidden fracture can alter the entire situation overnight. For 3i Atlas, these uncertainties are even more profound. Its nucleus might be as tiny as 320 meters or as massive as 5 kilometers. The current data from Hubble and JWST provide the range, but its actual size is still unknown. The dominance of carbon dioxide in the coma is evident from the spectra. However, a complete list of its volatiles and its dust remains beyond our grasp for now. Lacking a definitive detection of water or other common gases, each new set of data continues to reshape our working hypotheses. The one thing we know for sure is that forecasts will keep changing right up until and even after perihelion. Looking toward the future, the next wave of surveys, especially the Vera Rubin Observatory's LSST, will certainly catch more of these cosmic wildcards. Consistent full-sky imaging is going to spot the faint and fast-moving objects that can currently go unnoticed. But even when we're in the LSST era, the science will be defined just as much by what we fail to see coming as by what our models are able to predict. For the time being, the wisest advice is to observe the sky with curiosity and to prepare for the unexpected. 3 Atlas, with its immense carbon dioxide coma that measures over 700,000 kilometers wide, is notable for its interstellar origins and its mysterious composition. As scientists continue observing these amazing objects, the 2025 swarm is set to test and greatly expand our knowledge of cometary behavior and solar dynamics, adding another new chapter to the developing story of our solar system.